In this video, we're going to talk about enzyme inhibition. There we go. And we're just going to start with some terminology. So first we have an inhibitor, which will reduce an enzyme's activity, and an activator, which will irreversibly inhibit enzymes. So inhibitors are usually reversible and activators are not. And when we talk about inhibitors, we kind of classify them based on where they bind or how they work. So first we have a competitive inhibitor, and this will compete at a substrate at the binding site. So right where the substrate binds, your competitive inhibitor will bind as well. And these usually look like the substrate, which makes sense. So here we have succinate going to fumarate. Well, if we have malonate, which looks a lot like succinate, this can bind your enzyme and then you'll have no reaction. That's basically how Tamiflu works. So you take Tamiflu and in the liver you process it. Now this looks like a molecule that can inhibit the flu. So that's basically what Tamiflu is. You can also have product inhibition, where you have so much product, you bind the active site, and you stop the reaction because your substrate can no longer bind because your product is overwhelming your enzyme. Another type of inhibitor is a transition state analog, and these are very good because remember we talked about how enzymes want to bind tightest to the transition state. So if you have a molecule that looks like the transition state, this will be able to bind to your enzyme very well. Adenosine deaminase, if you look here where you have adenosine going to inosine, what you can inhibit this with is 1,6-dihydroinosine, which looks a lot like our intermediate state, except we don't have an NH2, we just have an H. That's the only difference. This can bind to our enzyme and inhibit this reaction. So that's a transition state analog inhibitor. Now let's look at the kinetics for these reactions. So we're going to look at competitive enzyme inhibition first. So we need to talk about Ki, which is the inhibition constant, which is equal to free enzyme multiplied by enzyme divided by enzyme total. So this is the inhibition constant for inhibitors. It's your dissociation constant. And since it's a dissociation constant, that means the smaller your number, the stronger the binding. So a very good inhibitor has units of nanomolar and picomolar, which is saying you bind to the enzyme extremely strong and you stop the reaction from happening. Now, since we're adding a new wrinkle to our kinetics, a new molecule, we need a slightly different Michaelis-Menten equation. And so here we have initial velocity equals V max multiplied by S divided by alpha Km plus S. So this alpha is due to our inhibitor. So alpha equals 1 plus inhibitor, concentration of inhibitor divided by Ki. All right. So that is how our kinetics is changing. In fact, the only thing that is changing is Km. Vmax doesn't change, but Km does change. So you can either call it alpha Km or Km apparent. You will see it both ways. And to understand why Km changes and Vmax doesn't, let's look at the mechanism that's happening here. So our inhibitor, our competitive inhibitor, is binding with free enzyme. So enzyme plus inhibitor, Ki, equals EI plus S, no reaction. Or the free enzyme could bind with the substrate and you do normal Michaelis-Menten inhibition. And the idea is the more inhibitor you have, the bigger constant of alpha, and the more your enzyme and inhibitor will want to bind to each other. Well, since these two are competing with each other, though, if you add enough substrate, you can outcompete the inhibitor and have only ES complex. But with the more inhibitor you have, the more substrate you need to outcompete your inhibitor. That is why Km is changing. Km is actually increasing here, because Km is half, or the amount of substrate you need to go to half your maximum velocity. As we see on this graph, the more inhibitor we have, the bigger the value of Km, because since we're competing, if we have inhibitor, we need to add more substrate to compete with our inhibitor, and so we need more substrate until we go to half our maximum velocity. But Vmax and turnover number are unchanged. We can use LineweaverBurk to determine our constants for competitive inhibition. So here it's like the previous LineweaverBurk. 1 over initial velocity equals alpha Km divided by Vmax, 1 divided by S plus 1 divided by Vmax. Your y-intercept, 1 divided by Vmax. Your x-intercept is negative 1 over alpha Km. So you can tell how your Km has been changed. Remember, alpha is 1 plus inhibitor concentration divided by Ki. So let's say you do an experiment and you measure what Km is by itself, so no inhibition. So you figure out Km. Then you do an experiment where you know the amount of I and you measure alpha Km. So you can solve for alpha. If you solve for alpha and you know the amount of inhibitor that you use, you can then solve for Ki by using a LineweaverBurk plot. Alright, the next type of inhibition we're going to look at is uncompetitive, which is Ki and it gets this prime. So first let's look at this reaction. Enzyme plus substrate goes to enzyme substrate complex. So uncompetitive binds this enzyme substrate complex. It doesn't bind free enzyme, so you're not competing at the end for free enzyme. Rather, it just binds your enzyme substrate complex. And if we do a LineweaverBurk plot for this, we get parallel lines. That is because both Vmax and Km are changing. They are both being lowered. You're lowering your Vmax and you're lowering the Km. And you can't compete this one. The more substrate you add, you're just going to make ES, but it doesn't matter because this enzyme binds to ES. And since you're binding to ES no matter what, that's why your Vmax is going down, where the amount of enzyme total is actually less than it appears, and so overall you're going slower. Your Km also decreases because your Vmax is decreasing, and your substrate is also decreasing because it's binding to the substrate complex. It's more difficult to actually rationalize why Km is going down, but for us, we need to just keep in mind in uncompetitive, both Vmax and Km are decreasing. And you see uncompetitive enzyme inhibition for multi-substrate enzymes. So here we're looking at normal Michaelis-Menten one substrate, but you will really see this for multiple substrates. The next one, and the last one we're going to look at, is called mixed or non-competitive, and this is an interesting case. Here your enzyme can bind either to the free enzyme or the enzyme substrate complex. It binds to both. And since it binds to both, you have a Ki and a K prime I. And the LineweaverBurk for this is that your Vmax will always decrease. So Vmax will decrease. But Km, we don't know what's going to happen with Km. It can either increase, decrease, or stay the same. And it really does that because Km is, if you look at your x-intercept, is A prime divided by A Km. So whatever A and A prime are, which are based on our Ki's, Km can increase, decrease, or stay the same. What we need to know from this, though, is that when you look at a LineweaverBurk, if you have your lines crossing at a point that's not on one of the axes, that's mixed enzyme inhibition. So here we have our line crossing, not on one of the axes. we have non-competitive. Vmax is decreasing, Km is doing something. We don't really know what it's doing. It can increase, decrease, or stay the same based on our two constants here. And this table is just a summary, so I would advise you to look at this table, know the Lineweaver-Burk equation, and know what the effect of the inhibitor is, and know if I give you a Lineweaver-Burk, are you looking at a competitive inhibition, uncompetitive, or mixed? That's it for this one. I will see you in the next video.